to the river course. If I look from the above the river course, the velocity vector is more or less tangential. So this is why, in order to identify a location, I cut the river with a perpendicular to the river course, the river bed. I said that the correct definition is perpendicular to the velocity vector, and you may say, yeah, but you just said that the velocity vector is not constant in a water body. True, and therefore I should say average velocity vector here. Now, behind what I'm saying, there is the theory of fluid mechanics we are not interested in. Maybe that you got some fluid mechanics in your background, and if yes, you perfectly understand, you already know what is a river cross-section. If you didn't get it, don't worry, because you don't need it to take this subject. So I'm just assuming, I'm just giving to you the basic concepts, and if you wanna get some details, you have all the means on the web and in the links in my web pages. If you are not interested, it's absolutely not a problem. So we get this river cross-section, and when we depict it, it's something that looks like this. Okay, and the water surface in a river is assumed to be horizontal, and it is horizontal when if there are no bends in the river course. If you have bends, if you have very visible curves, then the water surface may become a little bit tilted, and this usually doesn't happen in rivers, but it may happen in artificial channels. We assume that it's horizontal, again, through fluid mechanics, we make this assumption. And then we want to measure in this cross-section how much water is there. And in order to do that, I need to measure the river flow. River flow. Some synonyms: river discharge, or you may say water flow. I normally use river flow or river discharge interchangeably. For me, they are synonyms. What is the river flow? Typical question, it may happen in the exam, that I ask you, what is a river cross-section? What is a river flow? And this is something that you have to know. River flow is extremely important to us. So the river flow is volume, I'm writing while I speak, volume of water per unit time, passing through a given river cross section. So volume of water per unit time that passes through a given river cross section. It's very clear. Very clear. Of course, from that river, you cannot get more water than the river discharge. You have to take less. It can be proved, we don't demonstrate it, that the river flow is usually called with the symbol, identified with the symbol QT. It can be proved that the river flow is given by the product of two quantities, two other variables. So let me identify, first of all, the area of the river cross-section A, depending on T. So I use the symbol capital A to identify the area of the river cross-section. It depends on T. Why is that? Because it's the water level that depends on T. It depends on time. Okay, so the river flow is given by the product of AT times average velocity at time t in the river cross-section. Look, velocity here only depends on time. Why is that? Because it's already specified the location, the position in space. It's the river cross-section. It's an average velocity of fluid particles in the given river cross-section. Depends on t, of course, on time. It can be proved then that the river discharge or river flow is given by the product of the wetted area of the river cross-section, wetted area because it's wetted, times average velocity of the flow in the river cross-section. And keep in mind this relationship because it's extremely important for us. Why it is extremely important? Because we just said that we need to monitor our water body, and therefore we understand that we need to measure the river flow in order to understand through an inductive approach how much water is there. But the river flow, it's very difficult to measure. Look at the definition. Volume of water per unit time that passes through the river cross-section. How can you measure it? If we are talking about a tap, it's easy to measure. And this is how we measure indeed the river flow through a tap. If you want to measure the flow that your tap can deliver to you, it's very simple. You take a bottle of 2 liters capacity, and you open the tap and you measure the time the tap needs to fill the bottle. And then you divide 2 liters divided by the time that you just measured, and you have an average flow of your tap during the time needed to fill the bottle. But if you go to a river, how can you capture all the water that goes through? It's impossible. Unless it's very small, like a tap, but then it's not technically relevant. If it is a river with a certain size, it's impossible to capture all the water. So the moral of the story is that the river flow cannot be measured directly. It's not a variable like temperature, like velocity of the river flow that you can put an instrument in it and measure it. The river flow, it cannot be measured directly, and therefore we need to measure it through this relationship. So we measure the wetted area. This is easy. We call a surveyor, and then the surveyor goes over a bridge and measures the depth of the river along several verticals, and then we can get an estimate of the area of the wetted area. So we can measure it. And then velocity. Velocity is easy. You can measure the velocity of a river with very simple instruments. Let me see if I can easily find, if I have a good connection. With an instrument that, no, this is Mulinello, it's for fishing. Let me see. Still, let me see if I can see. Okay, here it is. Here, this is the instrument that we use to measure the velocity in a river. It's called in Italian Mulinello, and in English I think it's simply velocity gauger or something like that, or fish. Some books call it the fish. But basically, you know, there is this device that rotates with increasing velocity of rotation for increasing velocity of the flow. So the surveyor, while he measures the depth of water along the verticals, he can use also the Mulinello to get the value of the velocity, and then he gets an average value of the velocity, and then the river flow is measured. This is still a bit complicated because you need, at each considered time step, you need a person going there taking measurements. There are then some simpler measurement methods, but we don't go into the details. I just would like to tell you that these simpler methods derive the river flow by just measuring the water level. So they measure the water level, and they measure the water level with, in English it's called staffs. River staff. Let's see if I can get it. Yeah, this is a staff. This is a staff. They measure the water level with this kind of... if you look under the bridges, you see many of them. And now we use also electronic instruments. But in the past, they used these staffs to measure the water level. Okay, so what we get is, at the end of the story, a time series of river flow. And then we realize that the story is very complicated because once we have this time series of river flow, we understand that the river flow is affected by a lot of variability. Variability means seasonal variability, or, as I said, interannual variability. And we have to decipher this variability. And of course, the higher the rainfall, the higher the river flow. River flow is fed by rainfall or by snowmelt, but at the beginning there is some precipitation. Rainfall is part of precipitation. Precipitation is rainfall, snow, and other forms of precipitation. I don't know how to say in English, but it's any form through which water from clouds gets in touch with the earth, including fog. Fog is a way of feeding the earth's surface with water. An important thing, an important definition. I said rainfall, precipitation. Precipitation over what? For a given river cross-section, with some difficulties, you can identify a portion of the Earth's surface such that any and only the water collected there contributes to the river flow. I say again, for any river cross-section, you can identify a portion of Earth's surface such that any and only precipitation falling there contributes to the river flow. I think, now we check, I think this definition is in my web pages. So a portion of Earth's surface such that any and only precipitation falling there feeds the river flow. This portion of Earth's surface that refers to a given river cross-section is called catchment or watershed. It depends on the use of American rather than English or rather than UK English. Catchment is American English, but it's used also in the UK. Watershed is UK English. Some say river basin. It's another synonym. But the most used term is catchment. In Italian we say bacino idrografico. So keep in mind the definitions of catchment, river cross-section, river flow. I may ask them at the exam. Okay. Okay, good. So, again, variability. We realize there is variability. And therefore, we need to understand it, as I said. A first consideration, in order to understand variability, we need a long time series. We need a long observation period. Another term that it's better to remember, observation period. It's very easy, it's intuitive. Why a long observation period? It's obvious because if there is variability, it means that you have changes from one year to another, from 1 month to another. And therefore you need a long collection of years to understand what's going on. You may ask me how long the observation period should be, and well, it depends on variability. If variability is very large, you need a longer observation period. If the river flow is close to steady, which rarely happens, you need a shorter observation period. Usually we say that in order to understand low flows, we need at least some 10 years of daily or monthly observations. And by saying that, I introduced another concept, the concept of time step. The time interval between one observation and the next one. To describe a river, we usually use daily time step. Daily observations. Every day somebody goes there and looks at the water level in the stuff. Or every day there is an electronic instrument measuring the water level. In this case, we may talk about of hourly time step. Hourly means every hour there is an electronic instrument measuring. So I mentioned variability. Let me show you a figure that is, I'm very proud of it, but it's not exceptional. But I did it with R, so it's also an opportunity to show you. But I think I probably already showed you, and we didn't. I'm sorry because I am teaching two courses, so I make confusion. Did we have already a session on the PC in this? No, correct? Okay. So first of all, let's plan it, and I think. Next week, I'm not sure, on Thursday we have lectures, probably not. There are degrees, it's degree day or not. Let me check. So I take the opportunity to let you to breathe a little bit, because I know that I suddenly passed from descriptive topics to topics that are more. Let me see if I put in my calendar the 14th. Yeah, you see that I didn't put in the calendar March 14 because it's degree day, so I cannot teach next Thursday. So on Monday, please bring your laptop with you, because I wanna start with or let me think about it. Yeah, I think it's a good idea. Bring your laptop with you. I wanna start with the exercises. I think I already mentioned to you what software we will use, which is R. Okay, I mentioned it already. Yes, perfect. And if you please, if you can get on Monday with R installed, just installed. Don't open it, because we will do it together. But if it is already installed, it's better. And does somebody of you don't know how to install what I'm talking about? So you don't know about it, okay? So it's very easy. You should go to this website. Please go to www, and it's not easy to read, I know, and I'm trying to spell it. It's R minus, not underscore, minus project with the J .org. Can you read there? I hope so.
Yes.
Okay, and then you get here. You get here and you have to click on download. Don't lose time on the website for now, okay? Because it's huge, I mean. Go to download, and download, you see that actually you don't have to click on download, but on the CRAN, okay? And then select one mirror. I usually select mirrors that are close to here, but it doesn't matter today with the speed of the internet. So let me take Austria, and then let's wait a little bit. You see download and install R. So here you have download for Linux, for Mac, for Windows. And you take, for instance, for Windows, take the base, download R352 for Windows, okay? And then you may save it, double click, and it goes up. Good. So, on Monday, please bring your PC. On Thursday, no lectures. Okay? Fine. Let me go back here. And let me show you this figure that, okay, this is another example. Yeah, this is nice. Let me show it to you. This shows a combination of unconfined aquifer and confined aquifer. And there is a water layer, there is an impermeable layer dividing them. Unconfined, you see that it's in touch, it's connected with, possibly connected with the river. So it may happen that you have a connection between the river and the aquifer. And it may happen that the river feeds the aquifer, or it may be the opposite. And it may be a mix of the two, depending on the season. And the top of the aquifer, of the phreatic aquifer, is called water table. Okay? This is a figure that again refers to groundwater. It's not done by me. And this is instead done by me. Yeah, let me see if I can enlarge it. Okay, what is this? First of all, listen to me. Don't look at the figure because it's animated and it's distracting. This is the time series of the daily river flows of the Po River at Ponte Lago Scuro. Ponte Lago Scuro is considered to be the closest section of the Po River. Closest means the last section where measurements are taken, the last river cross section before the sea, before the delta. And here the idea was to plot it. Usually the time series are plotted in a 2D diagram. 2D diagram, basically you usually have, when you talk about river flow, let me see if there is a figure on the web which is easier to show. So, and you want to plot it, usually, here I am looking to Wikipedia. Okay, it's a bit. So here what you see, it's, okay, stream flow. This is another synonym that I forgot to tell you, okay. Stream flow on the vertical, on the ordinate, and day, Julian day means day in the Julian calendar, day in the abscissa, and this is what is called an hydrograph. It's a graph of the hydrology of the river. So it's a graph of a 2D graph, river flow along time. This is an hydrograph. And usually you see the river flow plotted in this way. The time series of river flow is plotted in the form very frequently of an hydrograph. And in this case, the hydrograph has the problem that if you refer to a long observation period, for the Po River is 90 years, it's difficult to capture the year-to-year variability, the interannual variability. Okay, you know, you can see it here, but you can see it here, you can see some variability along X here, along the abscissa, because it's a short series. But if you take the whole series of the Po River, you just see something that is difficult to interpret. So the idea was to depict it in a 3D diagram. And here you see the diagram is 3D because on the vertical you have the river flow. On the two horizontal coordinates you have one along the year, within the year, and the other one shows variability from here to here. So you see from 1920 to 2000, and here from 1 to 365. So you get a surface. So if you explore the surface along this direction, now it's rotating, it's a bit complicated, but if you go along this direction, is interannual variability. If you go along this direction, you are inside the year. So this is summer, low flow during summer. This is fall season, and this is June. So what you can see here, first of all, first note, the series is smoothed. Otherwise, it would look like a porcupine, something very spiky, and it's difficult to read. So in this case, it's smoothed, like you make it regular. But what you can see here is that you have one dry season in summer, another quite dry season during winter, and two high flow seasons in the Po River, which is true. The Po River is the expression, the result of a continental climate. It has two periods of high flow, spring and fall, and two periods of low flow, summer, winter. And if you see at the higher peaks, they are here in fall. But if you look at the spring season, there is more volume of water, which is what we know. In the spring season, it's difficult to have floods on the Po River, but you have a huge volume of water coming down. In the fall season, you get some floods occasionally, but the volume of water is lower with respect to spring. So you see that by plotting an hydrograph, you understand many things of a river. And in this case, it's a 3D hydrograph that it's, for some reasons, clearer. For other reasons, it's a little bit more complicated to understand. But still, you get an idea of variability. And there is another issue that comes clearly out from this figure, is that there are some periods where you have high flows, and I'm not talking about seasons. Like, if you look at the two extreme floods, let me wait for a while. Here they are. The highest blues, here they are. And you see that they are very close to each other. Here. 1, 2, 3. Indeed, we had two big floods in 1994 and 2000. Another big flood in 1951. It's here. No, it's it's here. And they seems to concentrate in some periods, like 94, 2000. At that time, people said, "Oh, this is climate change because two floods in only 6 years." But then, from 2000 on, for 20 years already, we didn't get any. And you see that there are other forms. Like here, there is a form that disappeared, and probably it's due to snow melt. And maybe that now we have less snow for global warming, maybe. And then we have less snow melt. If we look at average rainfall over the Po River, it didn't change much. Now it's already clear that climate change is not changing average rainfall. Maybe that it's changing the extremes. Scientists are debating on that. But average is not changed much. So we shouldn't be concerned about an average decrease of flows in the Po River. Or up to now. So understanding the time series is a way to assess water resources. But now we need to go to a quantitative assessment. This is qualitative. We look at a graph, we understand what's going on. Keep in mind that when you get a time series, when you get data, the first thing that you have to do is to look at a graph, to look at it. An engineer, this is the first thing that has to do. Look at it. A statistician looks at the statistics. You are an engineer, look at the figure, because it's the first step. You see if there are errors, if there are strange behaviors, which may be the result of a measurement error. Okay, and then you go to the math, to the quantitative assessment. Now let's move to the quantitative assessment. And for rivers, I'm talking about rivers now. And let's move then to the next lecture, which is assessing water resources availability, inductive methods. And let's start from rivers. Okay, there is the first part of the lecture that is descriptive. It's recalling concepts that I already discussed with you. And there is a brief history of water resources systems. It's a fascinating history. We are not interested in history of water resources systems, even if I must say that if you know the history of water supply, you understand why today we take certain decisions. And in some cases it helps you know, finding solutions. And I want to give you an example. I have 15 minutes, I think I can take 5 minutes to tell you a nice example. And you know that around the Middle Age, around 1700, 1800, there was a pandemic of cholera in Europe. And people didn't understand what was the origin, the cause of the cholera. So some people thought that it was a punishment by God. Some other people thought that it was brought by the air. They didn't realize that cholera was transmitted through water. And the reason of cholera was indeed the fact that the cities became larger and larger. People concentrated into the cities. And we already spoke that this was a first evidence on the possibility that development is unsustainable. They concentrated into the city, and then their wastes, they had the problem of how to evacuate the wastes, and in particular the fecal wastes. And they used to release them just in the soil. And this was the case up to a few years ago, and in some cities there is still this practice of releasing the waste in the soil because they don't have sewer systems. And they released waste in the soil, but the problem was that they were taking water from the soil, drinking water, and their wells were very superficial. They didn't go into the deep underground to take the water. Now it's quite common here to go to a depth of about 300 meters to get water. And in my house I have a personal well that is 80 meters deep, but my grandfather used to use a well that was 8 meters deep, so very close to the surface. They didn't realize that by releasing the waste in the soil, they contaminated the water, and this was the origin of the cholera, but they didn't realize it. So people were continuing to die, and the pandemic spread in all the major cities of Europe, including Bologna. And you know, they found the solution, they found the cause, because there was a medical doctor in London that in order to better understand what's going on, in order to investigate the causes, he started to draw on a map the case of death. And this is an example of observation. He started locating the cases of death, and he realized that a lot of the deaths were concentrated around a public pump, the Broad Street pump. It's a nice story. If you go to Wikipedia and look for Broad Street pump, there is the story. It's really interesting. And then he wondered why around the pump there were the cases, and also, and this is very interesting, he realized that some monks in a monastery were immune. So he couldn't understand that. But at the end, he realized that the pump was the problem. He didn't realize how, for what reason the monks were immune. And the reason is that the monks didn't drink any water. They used to make beer and drink beer. And by making beer, even if the water was contaminated, the fermentation basically eliminated the virus of the cholera. It's a virus? No, it's a bacteria, I think. The bacteria of the cholera. And this is really something interesting, you know. And this, the moral of the story, that we shouldn't drink water, you know that many people say that. We shouldn't drink water, but we should drink beer. But anyway, he was able to understand that the reason was water. And every time that I tell this story, people laugh. And I say, look, you're laughing, and that's fine, because 300 years passed. But if you think of the number of people who died for this, there is nothing to laugh, because it was indeed a tragedy. And so what I think is that probably now, today, we are dying for some unknown reasons, and the reason can be could be, I'm not sure, very trivial. And in 300 years from now, there might be people laughing at us because we died of cancer and we didn't understand why is that. And it's extremely interesting, this story. But anyway, let's go back to our problem. They realized that it was water, the problem, and of course they spread the voice over all Europe. In Bologna, there was the pandemic, and they tried to find a solution, because